Atomic number is the total number of protons in the nucleus of an atom. In chemistry, it is believed that chemical reaction is as a result of the alteration of the electron, since it is found outside the nucleus at the shell or at the orbital. According to Niebuhr, it is believed that there is a certain energy to which electron can be found. An electron can be identified by the use of 4 quantum numbers, which are 1, the principal quantum number 2, subsidiary or azimuthal quantum number 3, the magnetic quantum number 4, the spin quantum number. Let's start with the principal quantum number. This determines the energy level or shells of the electrons in the orbital. It has this discrete value or integral value of n as 1, 2, 3, 4, where these 1, 2, 3, 4 are mostly represented with K, L, M, N. To know the maximum number of electrons that can be found in a particular main energy level, the code is 2n raised to power 2. But n raised to power 2 alone tells how many degenerated or equivalent orbitals that are present in a particular main energy level. For instance, if we have n equal to 1, we will have 1 raised to the power of 2, which is still 1. Therefore, we are going to have only one degenerated orbital, and this is what we call s orbital. If we have n equal to 2, it gives 2 raised to the power of 2 gives 4. There are 4 degenerated orbitals, which are 1 s orbital, 1 px orbital, 1 py orbital, and 1 of the pz orbital. For instance, if we still go on with like n equal to 3, we will have 3 raised to power 2, which will give us 9. Here we are going to have 1 s orbital, 1 px orbital, 1 py orbital, 1 pz orbital, and we are going to have a dxy orbital, a dyz orbital, a dxz orbital, a dx raised to power 2 minus y raised to power 2 orbital, a dz raised to power 2 orbital. 2, the subsidiary or azimuthal quantum number L. This depends on the value of that principal quantum number I just said. It has discrete values from 0 to n minus 1. That is, if the value of quantum number is n, we minus 1 from the n, we have the subsidiary. For instance, if you have n to be 1, therefore we're going to have 1 minus 1, which will give us 0. If you have n to be 2, we are going to have 2 minus 1, which will give us 1. It shows the shape of the orbital. When the value is O, it is s orbital called sharp, but it is spherical in shape. When the value is 1, it is p orbital called principal. Its shape is a dumbbell shape. When the value is 2, it is the d orbital called diffused, and the shape is a double dumbbell. The fundamental is not well described. 3. Magnetic quantum number. This describes the splitting of orbital in the magnetic field. The values of m depend on the subsidiary quantum number. It ranges from negative of the quantum number from the azimuthal to the positive subsidiary quantum number. The formula is m equals to 2l plus 1. When l is equal to 0, we have 2 times 0, which is give us 0, plus 1. And this one, as the value is 1 s orbital, which is only s orbital. When l is 1, we have 2 multiplying 1, which is going to give us 2 plus 1. We have 3. Therefore, we're going to have 3 p orbitals, which is the p orbital written as px, py, pz. When l is equal to 2, we have 2 times 2 will give us 4 plus 1. We have 5d orbitals, which is the d orbitals dxy, dyz, dxz, dx raised to power 2 minus y raised to power 2, dz raised to power 2. If L is 3, then you know the answer is going to give us 7 f orbital. Note, each suborbital can accommodate only a maximum of 2 electrons, which spin in opposite direction, one pointing head up, the other pointing head down. The maximum number of electrons for S is 2, that of P is 6, that of D is 10, and F is 14. But based on our level in chemistry, we only focus our attention in SPD. The F is mostly ignored. Even towards university year 2, it is mostly ignored. Let's go for the fourth quantum number, the spin quantum number, S. This gives the direction of electron spin. We have these two values, minus 1 all over 2 and plus 1 all over 2, where we take the plus 1 all over 2 to be clockwise and that of minus 1 all over 2 to spin anti-clockwise. Let us go further with the electronic configuration, but we have to look at the 3 rules we are to follow in filling electrons in each orbital. 1. Auerbach principle states that electron enters into orbitals of lower energy first until it is completely filled before electrons can occupy orbitals of higher energy. From this rule, it will be good enough for you to know the arrangement of orbitals in their order of increasing energy. Another way of doing this is this. Whether you are to know it by this or this, just note the arrangement is always 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. I know you notice abnormality at 4s coming before 3d, where it's supposed to be 3d coming before 4s, and also 5s coming before 4d. Yes, it is so. It is not a mistake if you have followed the second way of arriving at 8. Let's go for Pauli exclusion principle. This states that no 2 electrons in an atom can have the same set of all 4 quantum numbers. This statement means the maximum electron an orbital can accommodate is 2, and the 2 electrons in the same orbital must have opposite spins. The Hund's rule states that electrons occupying degenerated orbitals singly maintaining parallel spins before they pair up. Take example with atom that has 5 electrons to be filled at the p orbital. It will be filled singly as this. Then the other is filled. Let us have elements and their electronic configuration filled. We have 2 ways of filling electrons, which is using shell and orbital. When shell is used, it is easier for students to predict the possible common ions. When orbital is used, it is easier to predict the number of unpaired electrons. Let us start with the SPDF electronic configuration. Mind you, WAEC and NECO prefer this SPDF. But I tell you, whenever you are asked to write electronic configuration of an element or an atom, and they did not tell you to use SPDF or the shell type, please, first of all, use the SPDF, then the second, the KLMN pattern. Recall, the highest value for S is 2, P is 6, G is 10. we can ignore the F, which is 14, because we are not going to make use of it. I think I have not seen a question that has to do with F. Example, write the electronic configuration of atoms with the atomic number 8, 17, 24, 37. I would like to show you properly how these are being done. Check for the second. Okay, check for the third. I hope you understand. Any element in which its last electron ends at s orbital is called s block element. If it ends at p, it is called p block element. If it ends at d, it is called d block element. If it ends at f, it is called f block element. Let us look at this other worked example. Find the number of lone paired and unpaired electrons in the following atoms: oxygen, nitrogen, calcium, and phosphorus. I want to use this to show you how to calculate unpaired electrons and lone paired electrons. Solution: for oxygen, the 1s is lone pair, that is in 2. What I mean by in 2 here is that the electrons are in 2s, one pointing up, one pointing down. We go to the 2s, that is the second energy level s orbital. We are going to have also one paired electron. If you go to the p orbital, the first p orbital, which is our px, we have a paired already. Therefore, we are having 3 paired electrons, but the remaining 2, as you can see, are unpaired. For nitrogen, the s orbitals are paired, the p orbitals are not, giving rise to 2 paired electrons and 3 unpaired electrons. If we go for the calcium, calcium has no unpaired electrons. It has 10 paired electrons. If we go for phosphorus, which is just like nitrogen, but has 6 paired electrons and 3 unpaired electrons, then I would like you to try the following questions. Let us fill electrons using KLMN shell. You should note that we are to use K equal to 2, L equal to 8, M equals to 8, but N equal to 18. This is because we are to follow this with the periodic table, where the shell represents each period in the periodic table. Okay, already filled. Let us take this example as a special element. Write the electronic configuration of the following elements: sodium, sulphur, calcium, and chlorine, using KLMN shell. Here we are going to do this with KLMN shell. For sodium, the atomic number is 11. That is to say, since sodium is a neutral atom, it has 11 protons and 11 electrons. But we are filling only electrons and not protons. Since the protons are inside the nucleus, but electrons possibly outside the nucleus, 11 electrons are to be filled. Give 2 to K shell, we have the remaining to be 9. Give 8 to L shell, the remaining is 1. Give it to M shell, we have 2, 8, 1. For sulfur, the atomic number is 16. It is a neutral atom and not ion. They did not say it is ion, they say sulfur, they did not say sulfur ion. Therefore, the electron number is 16. 2 to K shell, 8 to L shell, and 6 to M shell. We have 2, 8, 6. For carbon, the atomic number is 6. Give 2 to the first shell, which is K, and 4 to the L shell. We have 2, 4. For the chlorine, the atomic number is 17. Give 2 to K shell, 8 to L shell, 7 to M shell, it becomes 287. Focusing our attention at the already filled electronic configuration of elements. Any one apart from hydrogen and helium from atomic number 3 to 20 that ends in 1 is said to have a valence electron 1. If it ends in 2, it is 2 valence electrons. If it ends in 3, it is 3 valence electrons, and so on. The number of valence electrons determines the group the element is placed. If the valence electron of the first 20 elements ends at 1, it is grouped at group 1 because their valence electron is 1. If the valence electron is 4, it is group 4. If the valence electron is 7, it is group 7. But if the valence electron corresponds exactly the required or the maximum electron needed, it is said to have a valence electron 0. We render the group 0, which are the rare and noble gases. They are mostly inactive elements because their duplet states like helium and octet states like neon and argon are completely filled. Using the SPDF, if for instance the last electron ends at S1, we say that the element is in group 1. If it ends at S2, we say the element is in group 2. If it ends at P1, the element is in group 3. P2, group 4. P3, group 5. P4, group 6. P5, we say it is group 7. And when we have it as P6, it is the same thing as the noble or rare gases. But if, for instance, while we are filling, the electron ended at D, it is called D block element or transition element. We don't group them to anything like group 1, group 2, group 3. If we end at F, we say it is F block element. No need saying this is group 1 in F, group 2, group 3. I hope you get me here. Any valence electron that is below 4 using the KLMN is said to be metal and they ionized by electron loss. They lose their electrons to form ions like sodium is 281. The valence electron is 1, as you can see. Sodium valence electron is less than 4. Therefore, sodium is a metal and will lose 1 electron to form sodium ion, written as Na superscript plus. The number of electron an element lose is the number of its charge. Since sodium only lost 1 electron, the charge is plus 1 and the valency is 1, an absolute value of your charge. That is what we mean by the valency code. But valency actually means the combining power of an element or ion or radical. For magnesium, we have 282. The valence electron is 2. Magnesium forming ion will lose 2 electrons to form a positive ion as magnesium 2 plus. Since it is 2 electron, it is losing. Note that the valency will be what? 2. Because I say that it is an absolute value. Plus 2, we ignore the sign and just call it 2. For aluminum, we have 2H3. The valence electron is 3. Aluminum forming ion will lose 3 electrons to form a 3 plus ion. Since it is 3 electron, it is losing. A general way of representing this is M tends to give us m raised to power n plus n electron minus. Therefore, the number of electron gives us the number of charge, and that is called oxidation. Don't say you are to wait till you be in your SS2 for you to know what oxidation is. Oxidation is loss of electron. Each charge increases from 0 to the positive value of the number of electron it lost. That means that if we lose 1 electron, our charge become positive 1. Then if we gain 1 electron, I believe it's supposed to be a negative 1. Generally, group 1 is plus 1, group 2 is plus 2, group 3 is plus 3. And their valencies are 1, 2, 3 respectively. When we are to look into rules of naming compound, we always have this in mind that group 1, group 2, group 3, their name remains like that. You don't insert their oxidation state, because if you say sodium, we know that sodium is already in group 1, therefore the oxidation state is going to be 1. If we say magnesium, we know that magnesium is already in group 2 and the oxidation state is going to be 2. If we say aluminum, we already know that aluminum is in group 3 and the oxidation state must be 3. But any other element that is not found in group 1, group 2, group 3, when we are to name its compound, we insert the oxidation state of that particular element. Let us use sodium as an example. The atomic number of sodium is 11. It means sodium has 11 positive charged particles, which we call proton, and 11 negative charged particles called electron. We have 11 positively charged plus 11 negatively charged. If we join it together, that gives us what we mean by a neutral atom. That is for sodium as a neutral atom. But when sodium is forming a ion, which it is only the electron that participates in chemical reaction, as also in formation of ions. Therefore, sodium will lose 1 electron from its 11 electrons or from its 11 negatively charged particles. If we remove 1 from 11, what will remain is 10. Therefore, we have 11 positively charged and 10 negatively charged. If we are to put it together, we will have a remainder as plus 1. If you do so with magnesium and aluminum, you will know that magnesium has plus 2 and aluminum has plus 3. For valence electron that is 4, it is either minus 4 or plus 4, because most times it is difficult to give out 4 when you actually needed 4. But elements found here mostly form covalent bond, therefore they share with one another, like carbon, silicon, tin, and lead. While for valence electron between 5 and 7, that is the valence electron that is above 4 but below 8, the elements prefer accepting electron to complete their octet state. For instance, sulphur is 2 it needs 2 electrons to complete its octet state, but the total positively charged particle is 16. The negative charge is 16. If 2 electrons are added to 16 electrons, it becomes 18 electrons. Therefore, if we have 16 positively charged plus 18 negatively charged, this will give us minus 2. Therefore, sulfur is minus 2. Do same with chlorine and nitrogen. Look at the following works. The number of electrons is 8, proton is 8, neutron is 8, mass number is 16, since it is not a ion, rather it's just an atom. The number of electrons is 10, proton is 12, neutron is 12, mass number is 24, since the charge is plus 2. Therefore, to get electron in a charged ion, just subtract the atomic number from the charge to get the number of electron. Example, for plus 2 minus 12 will give. Remember that the negative sign is actually for the electron, therefore we have 10 electrons. For minus 2 in sulfur ion, we have minus 2 minus 16 will give us 1. I really thank you for watching this video on my YouTube platform, and don't forget to click the subscribe button if you haven't. But if you have, make sure you share this link to your friends through your social media platform.